Hello everyone, I am Dhaval Thakkar from Team Green Matrix. India's renewable energy capacity is growing rapidly, but there is a critical gap. You can't accurately predict how much power a solar or wind plant will generate in the next few hours. This leads to a grid instability, curtailments of clean energy, and financial penalties for generators. Karnataka alone curtails about 8% of its renewable generation because of unpredictable output. So we have a VidyutDrishti which solves this. It's a complete edge to insight system built which forecasts the renewable power output 1 to 24 hours ahead using real sensors, machine learning, and a local AI assistance, all running on premise with zero cloud dependency. Okay, so here's how the system works end to end. I have a two sensor uh, nodes here, one for solar, which monitors using seven sensors, one for wind with five sensors. Each runs on ESP32 microcontroller. Every 2 seconds, they publish sensor data over Wi-Fi using MQTT protocol to a Raspberry Pi, which act as a edge gateway. It stores everything in database and serves it via REST API. A laptop running the dashboard pulls this data, runs ML forecasting models, and provide an AI chat assistance, all locally. No data ever leaves the system. Okay, so let me show you the hardware and let's go a little bit detail into that. This is my solar monitoring node. We have a BH1750 here. It measures the light intensity, which we convert to a global horizontal irradiance or GHI. This is the primary driver of solar power output. We have a BME280 here, which is a 3-in-1 sensor giving us air temperature, humidity, and barometric pressure. So we have this small module here, which is GY906, an infrared thermometer that measures the solar panel surface temperature without touching it. Every deg- every degree above 25 centigrade reduce the panel efficiency by about 0.4%. We have a ACS 712 here. This is the Hall effect current sensor. It measures actual current flowing from the panel. We have the solar panel here, and I have the novel approach for soiling detection on the panel. We have the laser beam bounces off the sensor and we put that on the panel so it bounces off the panel surface, and we have the LDR sensor which measures how much light reflects back. A clean a clean panel reflects strongly and a dirty panel absorbs it. So this gives us a soiling index from 0 to 1. We also have the OLED display here which shows all the reading in real time on the node itself. And we have the wind monitoring node here. So it has a two potentiometer, one for basically one simulate an anemometer and another one wind vane. In production, we will swap this with the real instrument. The firmware code that we have on the ESP32 reads the same GPIO pin, so it do not require any code change. We have a BME 280 here for wind node as well. Basically, it gives pressure and temperature to calculate real-time air density because wind power depends on air density and not just speed. And we have MPU 6050 here. It's a six-axis motion sensor measuring vibration in real time. So in wind turbine, high vibration indicates bearing wear or blade imbalance. enabling predictive maintenance. And we have the OLED display here for WinNode as well. So here's the raw data flowing. So you can see here on the terminal, we have the raw data moving from a sensor. Sorry, let me get that thing back. So we have a raw data flowing from the sensor. We have different factors that we are capturing for solar, GHI, a panel, temperature, a power, a soil. For wind, we are considering wind speed, direction, power, and the vibration. We will see more into detail how this data is being useful for our solution here. Okay, so let me just go to the dashboard to understand how we are using those data that we just saw in the terminal. So right now, let me switch to the solar first. Uh, so you can see a GHI here, power output, a panel temperature, soiling index, humidity, and current. So this BH1750 measures the light intensity, the primary driver for solar power, as we discussed earlier. Watch what happens when I shine the light on top of it. So we can see it is uh, jumping. A GHI is jumping on the dashboard, right? We see it went to 8. That's the direct relationship. More sunlight equal to more power, and we are seeing the power output increase as well onto the dashboard, right? We have the soiling sensor here that we said. Uh, so laser, as we discussed, laser bounces from the panel like this, and the LDR sensor will detect how much reflection it is getting back. Uh, we, Basically, in testing, if we have a dust on the solar panel, it soiling. So basically, in the dashboard, soiling index jumps from zero point 0.1 to zero point 0.8. Uh, Forecast drops, and we send the automated cleaning alerts. So we have a different set of graphs here as well on the dashboard as well. So now I'm switching to a wind node here onto the dashboard. So you can see wind speed here, wind power, wind direction, vibration, and air temperature, air density on the dashboard. So the green potentiometer is simulating wind speed. Watch the dashboard as I increase the gauge of it. So now we can see the wind power is getting increased and it is climbing fast. And let me also change the wind direction here. So we can see it is changing the direction here as well. So the wind speed increases and it also increases the wind power. Let me decrease a little bit from 5.2 to, let's say, 3, around 3, and we can see the wind power also decreased. So we have a scatter plot on the dashboard which shows the actual data flow following the cubicle curve. Okay, so now let's check the MPU60 vibration sensor. So we have a condition like if the data is coming, vibration data coming from the sensor is less than 2, it's just the normal vibration. If it's between 2 to 5, it's a warning. And if it is more than 5, it's 5. If it's more than 5, it will be critical. So let me vibrate the sensor a little bit. Now we can see the vibration is getting increased onto the dashboard. It is going from 2 to somewhere around 7, and we can clearly see the vibration alert and vibration warning onto the dashboard. And we can see that on the plot and the graphs as well. Okay, so let me switch back to the solar, and we will see the forecast here. So now the forecasting intelligence. This is my XGBoost model predicting solar power 1 to 24 hours ahead. A gray line we have here is actual historical data, and a green dash line we have here is a prediction, ML prediction. The shaded area is a 80% confidence uh, interval. Conformal prediction, distribution free, no assumption, and verified, which achieves 80.2 actual coverage. We have the correlation here with GHI versus power and panel temperature versus power. Same kind of prediction we have for wind as well. And we have the wind analysis, wind direction versus speed, and speed versus power here. So let's check the model performance and the methodology we are using. So wider confidence band at a longer horizon is physically correct. More uncertainty further ahead. Wind result we have 13.5 MAP at 1 hour, 70% better than persistence, still beating the baseline even at 24 hours. The wind analysis tab, we saw the scatter plot and view cube curve. Uh, SAP confirms the wind speed dominant dominates the feature, matches the physics. And for wind, we are at like for solar we are like 9.1% MAPE for 1 hour. 88% better than persistence baseline, I can say. Okay, so that was about how we are predicting and all about the data flowing from the sensor and result and baseline. Now let's talk about the AI assistants that we have built in into the dashboard. It is running locally and it is using Qwen 2.57 billion parameter model running via Olama, no API call, no cloud, all data stays on premise. Currently it is running on a laptop, but in production we can configure it on a private network. The LLM has a full context, all sensor reading and forecast injected into the prompt. So it analyzes everything and gives us specific data backed recommendations. So let me ask LLM about what is the current state of both nodes and should I take any action. So basically this is for a plant operator if they want to interact with the data and they don't need to be a data scientist to interact with the data. So I asked what is the current state of both node and should I take any action. It is precisely saying that solar node is currently generating 0.57 watt with soil index of 1, indicates the panel is dirty. The forecast suggests an increase in power output over the next few hours, but immediate action for cleaning might not be necessary given the current low output. Right now, I am indoor and recording the demo, so that's why power generation is very low. But in the actual sunlight, it will giving the perfect prediction. And for the wind node, it's saying it is producing at 5.5 watt at 3 ms wind speed. The forecast shows a significant increase in wind power, which could potentially boost energy production. No immediate maintenance action are required based on the current reading and the forecast. So we vibrated the sensor a little bit. We haven't vibrated that consistently, so it is not suggesting anything around the vibration or the predicted maintenance for the for the wind turbine. So let me ask another question about when will the wind condition improves for better power generation. So based on the forecast, it says wind power output is expected to increase significantly over the next few years. By let's say 6 hour plus, the wind power is projected to reach 74.8 watt with a wide confidence interval. This suggests that within the next 6 hours we can expect an improvement in wind condition for better power generation. Still, uh, the training happened for the model on a synthetic data as well as 24 hours of wind. But if we train the data on the actual real-time condition, it will be way more accurate. It uses the forecast data and gives a time-based answer critical for scheduling. Grid operator need to know when to expect changes, right? And it is running completely locally, fully compliant with data security. No plant data ever leaves the system. Okay, let me go back to the slides. So we have a machine learning pipeline. We are doing the feature engineering across 93 features. We have a lag feature, rolling mean, and standard deviation. We have a temporal overlay with as a scene cost embedding and physics. We have clearness index at density. We are also injecting that solar power never goes in negative. We are, as we said, we are using the XG boost model, and we have a 5 horizons, 1 hour, 3 hour, 6 hour, 12 hour, and 24 hour ahead. And we have a separate model per node, solar and wind. 500 trees for the XGBoost tree. We have a depth of 6, learning rate 0.05, and we have a physics constraint post prediction as well. Conformal prediction, distribution free, uncertainty intervals, 80%, 90%, and 95% confidence band. Guaranteed coverage, verified with 80.2 percentage. No assumption about error distribution. We have a SAP explainability, per prediction, feature attribution. So we have a top drivers, GHI for solar and wind speed for wind, and we have physics consistent model learn. LLM translates SAP to a plain English, so that will be easy for operator to understand. We have the physics informed result, 9.1% solar MAPE as we seen on the dashboard, and 13.5% wind MAPE, and 88% solar improvement, and 70% wind improvement. So let's talk about the production deployment. For production at KRE, DL, and KSPDCL plants, each plant each plant gets an edge node, industrial sensor, Pi running ML inference locally. So in the prototype, we were using the potentiometer, but in the production, we will be using the actual anemometer and the wind vane to calculate the actual data. So the central server will be storing the sensor data into InfluxDB plus Grafana plus LLM, all on private network. So we don't use the public network onto the production. So what will be the impact out of it? Karnataka's 15 plus gigawatt renewable capacity, which is like 5% accuracy improvement, equal to more than 100 crore year saving in cur- uh, curtailment plus penalties. So to understand more about all this thing, I kept this demo a little bit brief, but if you want to see a detailed presentation and for complete deep dive into the architecture, methodology, and result, you can check the full presentation. I link that onto a hacker submission platform, and you can learn more about architecture, sensors, ML methodology, model performance benchmark, and production deployment plan in very much detail. You can go much deeper into physics informed feature engineering, conformal prediction, calibration, and SAP explainability result and LLM stuff. Thank you for watching. Have a nice day.